Hermit.
Hi, everyone. Can you hear me? I don't know if anything's on.
Hello. Is anyone doing anything back there? Test.
I can yell really loudly if people would prefer.
Hello?
No. Is it turned on? Yeah, it's on. I did that a minute ago.
The mic has been rebooted. Should I try now? Nope. Just want to double barrel it. Anything? Test 1, 2, 5.
Yeah, I'm just going to yell. What's that? Okay. If I talk like this, can everyone hear me? Yes. Awesome. So I'm a bearded guy from Kansas, and I'm going to talk about a bearded guy from Kansas. And I'm going to keep with the theme of the entire day so far and talk about a GHC plugin. So somebody once told me to start your presentation with something controversial. I'm going to do the exact opposite of that. I'm going to say that functional languages kind of encourage this idea of equational reasoning about your program, right? I don't think that's controversial. Richard Byrd wrote a book about it, and there's been a million papers that feature some kind of equational reasoning in them. And in the two most common cases where you'll see this in the world of Haskell, has to do with type class laws and GHC's rewrite rules. So type class laws are these properties that are expected to hold of the instances of a class. For instance, these are the laws that you would associate with the monad class. And you've got two unit laws and an associativity law. And typically, these things are specified somewhere, and you're supposed to prove them about your instance, but most people probably don't. Rewrite rules are a similar idea where you have this equational property where you say this expression, stream on stream of S, is equivalent to this other expression. Ooh. Yeah. We have power. Now I'm too loud. I don't know. Okay, cool. I can talk normally. So rewrite rules are these other common cases where you see these equational properties. And GHC applies them willy-nilly, and it doesn't try to verify that they're correct, because in most cases, how would it? And so if anybody goes to the trouble of reasoning about these properties and trying to demonstrate that they're actually correct, or that they actually hold for a given class instance, typically they do it by hand, and it's kind of a back-of-the-napkin type of calculation. Which is great that we can do this in Haskell. I mean, that's a strength of Haskell that you can reason so simply. But it also is tedious. And if you're doing it for anything more complicated than the standard instances of standard type classes, it gets to be pretty difficult to do by hand. It tends to be error-prone and not necessarily outright errors in the reasoning, but you might just gloss over details that actually turn out to be important when you do things by hand. And also, generally, if you do this at all, you'll do it once and say, okay, good, and then your program will change over the next 2 years and you'll never do it again. So it's informal. And an alternative approach is to transliterate your Haskell program into some language that does support automated reasoning. And then prove your properties in that language and say, well, if my transliteration is correct and I prove the properties in that language, then they also hold in Haskell, which is a whole wide area of expertise. And you've kind of lost that simplicity of the reasoning that you can do on the napkin. So, of course, I'm proposing to use something different. And I want to point out I've managed to put a bearded guy from Hermit, or a bearded guy from Kansas in every presentation I've given about Hermit now. So this is functional programmer patient 0, I guess. Hermit is just a GHC plugin that allows you to interactively reason about the core representation of your program. And you can do this interactively. You can script up your transformations of reasoning. And it comes with a big dictionary of transformations that we've already implemented for you. So hopefully it makes things easier. Previously, we've applied Hermit to a lot of transformational tasks. So we've written domain-specific optimizations. Connell Elliott used it to implement a prototype compiler to take Haskell to hardware descriptions. And then our original examples were mechanizing a lot of worker wrapper transformations from the literature. This was limited because you had to start with some expression and transform it into another expression. If you needed to repeat some reasoning step, you had to rerun the transformation in place. Like there was no real abstraction here. And preconditions were just generally ignored. For instance, if you want to float a case expression out of argument position to a function call, like there's a strictness side condition there, it was either ignored or you had to do this complicated thing where you passed in a transformation that demonstrated the strictness of the function. It was really just messy for doing that kind of thing. So generally, we just ignored those type of side conditions. So in this paper, we add this notion of lemmas to Hermit. And lemmas are simply, at their most simple case, they're just equivalences between expressions. So if you're familiar with GHC's rewrite rules, pretty much that. Okay. For instance, this would be the lemma that represents the map fusion rule that you see in every paper about fusion ever. So if you have a composition of two map operations, it's the same as mapping the composition of the functions, right? And you can see that lemmas have universal quantifiers. These quantify over expressions, none of the lemmas, so it's first order. And then we added conjunction, disjunction, implication. So you can actually do quite a bit with just that. So a more complicated lemma, which, sorry, it's getting over to the edge, but I promise you're not missing anything. Now we have many more quantifiers. Some of them are quantifying types, so M, A, and B there. One of these is the dictionary quantifier, and then these quantify over expressions. And you can control the pretty printer in Hermit to display the types or not display the types or whatever you want to do. I turned them on here so it's less like alphabet soup. So defining these lemmas, we initially started writing all this like ad hoc proof mode stuff. And then we realized, like, oh, wait, we already have this great DSL for transformations called Cure, which is what Hermit's built on top of. So we ripped out all that ad hoc stuff, and it actually turned out to be really nice to just write transformations on lemmas instead of transformations on expressions. And then also you can use lemmas as transformations. So just like GHC can apply rules left to right automatically, in Hermit you can apply lemmas bidirectionally. And you can, once you have a lemma, you can use it as transformation on your actual code. Also, the actual proof of a lemma is just transforming whatever the lemma is into the primitive truth value using whatever transformations we have available. Structural induction is another transformation that just takes a lemma and replaces it with a conjunction of all the base cases in the inductive case. And then you can use lemmas once proven to transform other lemmas to prove them. So this ended up being nice and clean, and we could just reuse a lot of Cure's things that we've developed, for transforming expressions. And since we can reuse all this, I'll get an interactive proof mode, and we can script it and do all the things that we could before. So I'm not going to go through everything we do in the paper other than these bullet points. I encourage you to read it, of course. So we talk about this new infrastructure a bit more in detail, what the structural induction notion is, the limitations, etc. We provide a small example demonstration. And then we have two case studies. One of them is verifying type class laws for a lot of the standard library classes and types. So, you know, monad instance for maybe, or we do the monad laws for a bunch of transformers. So there's that. And then we have another case study that mechanizes reasoning from Richard Byrd's book, which I'm going to show you one tiny example from to kind of demonstrate the type class law studies are mostly just unfolding simplification. So the Byrd book is a bit more interesting as far as reasoning goes. And then we also talk about how you can integrate this with Cabal to rerun, recheck your proofs every time you compile your program. So, which is just a nice side effect of working within GHC as a plugin. So this case study, which I'm missing part of on the bottom of the slide, but unfortunately it's not important, is a program for playing the century game, which is essentially a game where you take 9 numbers and you try to insert multiplication and addition to create 100. And in typical Byrd style, he writes this nice program that generates all possible solutions, or all possible permutations, and then checks for all valid solutions, and then just takes one of them, right? And then he slowly refines that using equational reasoning into an efficient implementation. So we just mechanize that. And at one point, I was hoping the resolution would be a bit higher. At one point, we have to prove this property, where if you filter all the good values out of a list, it's the equivalent of filtering all the good values out of all the okay values out of the list. It's not really important to understand what good and okay mean, just take it on faith that this is supposed to be true. In the book, this is just assumed. We actually try to prove it. So we can essentially just state that as a GHC rule imported into Hermit. You get this lemma right here. The only difference being that composition is prefix now. And to prove it, we're first going to appeal to something more general. Which I apologize that it's off the edge. Which is filter P is equivalent to filter P after filter Q if QX equals false implies PX equals false. If that's not immediately obvious, go with me on it. So you can use a rewrite called lemma consequent, which just essentially unifies the consequent of this lemma with the lemma that we're trying to prove, instantiates P and Q, and then leaves you with the antecedent to prove. So this is your typical, like, if you've done natural deduction in a class before, you're building your proof back upwards towards true, right? Kind of this reverse reasoning. And so you can just state that, and Hermit will figure out all the instantiation stuff for you by folding expressions. And so now your goal is to prove that for all x, okay value x equals false implies that good after value x equals false. So next step. So probably just want to unfold the composition. So we can do that with the strategy combinators that Hermit provides. We have essentially the same thing without composition now, or composition now. And we don't really care about the value function, so let's just abstract it away and do a new universal quantified variable, y. So now we just need to show that okay y equals false implies good y equals false. This proof pretty much follows what you would do by hand. Which is the whole goal. And then now we actually care about okay and good. Don't try to read that expression because it's big and it's on a slide and you're in a talk and it's in the morning. But essentially what this expression says is that we take y apart into some quadruple, and then we say that there's this some quantity that's less than or equal to c implies that that same quantity is equal to c. Sorry. some quantity is less than or equal to C is false, then that implies that the same quantity equal to C is also false. So if something's not less than or equal to the constant, it's also not going to be equal to the constant. So the next thing we might do is just try to prove by cases on Y. The two cases will be the undefined case, because Y could potentially be undefined, or when it's some quadruple of some other quantified variables. So there's a proof by cases command that does that. What it'll do is it'll generate a conjunction of all the possible cases. I don't want to show you that because it's longer than a slide. So I just use this smash command, which does this basic type of simplification stuff that the machine can automatically do. So it totally gets rid of the undefined case, hopefully. And it leaves you with this case where you're just left proving that some number less than equal to C equals false implies that that quantity is equal to C is also false, which is what we were trying to do to begin with. And now we can appeal to something in a library, which states that property for integers. Hermit has the ability to dynamically load these libraries of lemmas that have already been proven by somebody else. Right now, there is exactly 2 of these. There is this one for integers, and there's one for worker wrapper. I would like to integrate with some repository of proven properties at some point, but that hasn't been done. But you can dynamically load this. These libraries are just package, Cabal packages, so they're easy to distribute and write on your own if you want to. And then we just apply the lemma with that incredibly long name that is this lemma to prove this property. And you'll end up with true, which means you're done. You can end the proof. So I know that took a while to explain, and it took a number of slides, but it was really only 5 or 6 steps. And it's the same 5 or 6 steps that you would write by hand. So if you would like to download the entire case study, which features this and several dozen other small little reasoning steps that we've done, it's on the webpage for the paper, so you're welcome to go through and look and see what I mean. So the takeaways from the 2 case studies, I didn't show you anything about the type class laws study just for time purposes, but the takeaway from that was what I said earlier. It's mostly a lot of simplification and just reduction of expressions to demonstrate that they're equivalent, usually up to alpha equality. There are a few practical issues with working inside of GHC. Unfolding information is not always available, so we have to define our own instance of a pin, or our own implementation of a pin, for instance, and rewrite the library version into that. That's something that we could probably work around by changing the way GHC exposes unfoldings. I'd love to do that at some point. In dealing with the type class laws, you have to deal with coercions a lot because a lot of things are implemented in terms of new types. Thankfully, the smash rewrite has some built-in just kind of attempt to reduce coercions and combine them with other ones. That got us through the entire case study that we did. There's probably a more elegant solution to that problem in the future, rather than just invoking smash every time you get stuck. And then from the Century case study, the takeaways were mostly that you could do the reasoning in the equivalent manner that they could in the book. And in the book, they actually only walked through the proofs of 2 properties. We ended up proving all but 2. So we ended up proving about 8 extra properties that they didn't prove in the book. And we did discover an error in the textbook, not in one of the proofs, but in one of the definitions, but that's why you mechanize this stuff, right? So, and associativity is occasionally awkward. That led to some problems where, a human can look at something and just be like, oh, it associates this way. We have to actually do those steps in our proof. So in some cases that added, a small constant number of extra steps to manipulate the associativity of expressions. So to conclude, paper is attempting to demonstrate that you can do this type of reasoning during compilation on GHC core, which is slightly more complicated than Haskell when you throw in all the type and dictionary arguments. But you can still do it at the comparable level of abstraction that you can do by hand. And since Hermit is a GHC plugin and it integrates, with all the GHC ecosystem, you can, automatically recheck these things, so you can enforce this connection between your reasoning and your program over time, which is better than doing these things by hand. There's lots of work still ongoing. Andy and several of his students this summer have been working on a GHCI-based interactive mode. So right now we have this kind of hacky interactive scripting system that we came up with long ago, and we're replacing all that with GHCI, and you'll have proper Haskell DSL for specifying all your transformations. And we're really at the point where we need a good parser for core, so I know that is a rabbit hole that many people have fallen down and never come out of, but we're going to have to go down it again, I guess. And I would really like to connect this to other tools that reason about GHC core. There's several out there. HipSpec comes to mind. They tend to be automated, so I'd like to integrate them in so that way the user can appeal to them when they need to. And then in the future, we'd just like to scale this up to larger examples. So if people have use cases in mind, there's almost zero documentation for Hermit still, but it's all up there in my head, so you're welcome to email me, and I'm happy to talk to anybody that wants to. And with that, I'll thank you for listening.
Just a question about the proof you showed. This property of filter, you presented it as not Q implies not P, not Q of X implies not P of X. Well, you presented it as Q of X equals false implies P of X equals false. And I would have written it P implies Q. Is that there for a technical reason to do with the definition of filter that you've got? Or just
No, that just, I happened to type the letters in that order, so yeah. I think I probably started writing on the right-hand side and then worked out what the left-hand side would be, so that's probably why they're in the opposite order.
Do you have some formal underpinnings for Hermit itself, as in that what Hermit thinks is true is going to be true, and with regard to what semantics, if so?
So there's no formal logic or semantics underlying the transformations right now. Your ability to demonstrate truth is just entirely based on what you can transform. So all of the transformations that are available to you are just assumed to be correct and valid. I would certainly love to dive into that and at least prove some things are actually valid to use in all cases and some things aren't, and do that kind of thing, but it hasn't been done yet.
So I wonder if you tried to use a script or a proof on a slightly different program just to see how much has to change when you are proving effectively a slightly different theorem, maybe.
So the nice thing about having these universally quantified variables in these lemmas is that we can prove like a general property, like this property right here that I appealed to. We didn't just assume that, like I actually proved that as well. But that's like, you can generally use that in other cases, right? And you can use these commands like lemma consequent to apply them, and it automatically instantiates the variables and all that. So in that sense, the reuse story is a lot better than what we had before. You still, since this is all user-directed, you still have to, point to the point in your program where you actually want to do the reasoning and do that kind of thing. So we haven't done a whole bunch of work in taking one transformation and just applying it to a bunch of different programs. The best we've done there is automate the concat vanishes examples. Like there's several cases where you can apply the same concat vanishing transformation at an accumulating parameter. So we have one script that works on like 3 different examples of that, but
so did you say at the end that we'll be able to write tactics in Haskell, basically?
So hopefully once this GHCI-based interface works, instead of having to write in this scripting language that then gets translated into Cure transformations, you'll just be able to write the Cure combinators directly. And so they'll be type checked and all that. So.
So you mentioned this problem with new type coercions getting in the way. Have you thought about sort of doing reasoning at the level of representational equality rather than nominal equality, if I can put it like that, and so just sort of making those bits of the proof disappear?
No, I haven't thought about it. I think, I don't know. They'll work because somebody that's used to Haskell is probably not going to understand what's going on with them, right? And thus far, like I said, we've gotten away with just providing kind of a general, like, get rid of these type of transformation that attempts to do what it can to, like, move them out of the way so that way you can do what you want to do. But no, like, we haven't looked into redefining what we consider equality to work around them. So.
And do you represent the coercions sort of explicitly in the output? Because I didn't think I saw any examples of where the core coercions would.
I don't
actually
show them, but we use kind of the same syntax that you would see in Richard's core spec PDF, for instance, like the little right-hand triangle with the type equality on the right-hand side. So yeah, the pretty printer makes them look kind of nice, and you can abstract them so you don't have to actually look at them if you don't want to. But generally, it's important to know that they're there because your transformation may not work if they're in the way. So,
thanks very much.
Yeah.